Lesson 20, Polar Representations for Complex Numbers. In this lesson, we're going to be talking about complex numbers, as well as the other ways that we can represent or identify them, and their various properties. A complex number is a number that is often represented in what is called the rectangular form of a plus bi, where a and b are both real numbers, and I is the imaginary unit, or the square root of -1. The value of a is also known as the real part of z, or re parentheses z, and the value of b is called the imaginary part of z, or im parentheses z. We may then express the complex number z equals a plus bi instead as the real part or real component of z plus the imaginary part or imaginary component of z times I. This is just another way that we can represent and express a complex number. However, in many of the calculations you will see in this class concerning complex numbers, we very often will refer to the rectangular form as a plus bi. These numbers can be graphed on a plane similar to the rectangular or Cartesian plane that is known as either the polar or the Gauss plane, where the x-axis is instead relabeled as the real axis, and the y-axis is instead relabeled as the imaginary axis. We have a couple examples here on the right side. So for example, if we were talking about the complex number 1, or if you write that out fully as a plus bi, that is 1 plus 0i, that means you have 1 in the real direction and 0 in the imaginary direction. So that means we are going to go 1 to the right and 0 up or down. That leaves us with our point on the x-axis there. If we instead have the point on the y-axis down here, this is z equals -3i, or z equals 0 minus 3i. This means that we have a real component of 0 and an imaginary component of -3. So if we were to graph this on the Gauss plane, that means go 0 right or left, and then go down a distance of 3. Lastly, we have our other complex number, -4 plus 2i in the top left here. That already is in the form of a plus bi. Our a, or real component here, is -4. That means we go back 4 on the real axis. Then positive 2i means we go up 2 on the imaginary axis. Note when we are referring to the coordinates on the complex plane, or the polar or Gauss plane, we do not refer to either the first or second component having I on them. We are talking about the real numbers a and b. b happens to be multiplying the imaginary unit square root of -1, but we do not consider the imaginary part as the value of b and I, just b. Let's talk about now the modulus and the argument for complex numbers. To understand the modulus and argument of complex numbers, let us suppose that z is equal to a plus bi is a complex number. We then will say the modulus of z, which is denoted with vertical bars surrounding the value z, looks kind of like an absolute value, but is different, is defined by the modulus of z equaling r. The reason for this is if we are thinking about a complex number, if I write it on the complex polar plane, the complex plane would be the real axis and the imaginary axis. We can consider some point up here as, let's say, 3 plus 4i. Well, I can consider that in the rectangular fashion by going right 3 and up 4. That's the rectangular fashion. Or, instead of going right a distance of 3 and up a distance of 4, we could also consider how to turn towards that point from the center or from the pole, and what distance from that pole we have our value. Meaning, if I want to find the distance, which is what the modulus really represents, of the complex number from the pole on the complex polar plane, that is really just the value r. This should have a lot of parallels to what we've already discussed with the polar coordinate system, because this really is just polar coordinates. The modulus is just going to be the specific name for the radius, or the distance from the pole, when talking about complex polar values. And that also means that calculating r doesn't take anything more than working with the Pythagorean theorem. This is why, to find r, or the modulus of z, we just need the Pythagorean theorem, thinking about both the real and the imaginary component of the complex number. Now, for z does not equal 0, meaning we're talking about some complex number that is not just on the pole, so not the number 0. The angle theta we refer to as the argument for z. For z doesn't equal 0, meaning we're on the pole, then the argument really does not exist or is not defined. This is because if you have not moved from the center point, then there is not really a defined angle measure for how much rotation we need to turn for that point. However, since theta is just going to be called the argument here, but there's no difference between how we referred to the value theta in the polar coordinate system in the past, we are still going to calculate theta the same way. In this particular class, the argument will be presented as an angle between 0 and 2 pi in most circumstances. Between 0 and 2 pi. In other classes and sciences, you may experience the argument to be restricted within other intervals. For example, it is actually relatively common to see the argument actually listed to be an angle measure instead between negative pi and up to pi, instead of 0 to 2 pi. For simplicity, though, and also for connections to previous concepts, we're going to list the argument between 0 and 2 pi, like a usual angle measure within the unit circle. If we do want to calculate that angle measure, though, again, it's not going to be any different from what we did with polar in the past. As long as a does not equal 0, so as long as the real component is not equal to 0, then we can say tangent of our argument is equal to the ratio of b over a. This is very similar to thinking about what we've done before, where we said something like tangent of theta is equal to y over x. Well, in this case, b is just the imaginary component, and we write that similar to a y-axis, and x is the real component, and we write the real axis just like the x-axis. So it's the same relation there. If a equals 0, though, then you cannot use this because then you would be dividing by 0. However, we should be aware that if a does equal 0, if the real component is equal to 0, and the imaginary component is something else, for example, 0 plus 3i, then that means, similar to an xy plane, I'm going 0 left or right, I'm just going up or down some amount. Meaning that we are on the imaginary axis, either the positive or the negative. And in terms of angle measures, we should know that the positive imaginary, very similar to the positive y-axis, should be an angle measure of pi over 2, whereas the negative imaginary, or negative y-axis, should be an angle measure of 3 pi over 2. So if a does not equal 0, or if a does equal 0, just consider where the imaginary number is. If we have 0 plus 3i, we're positive imaginary, that means we're up on the y-axis, or the imaginary axis. My angle up there should be pi over 2. If I was working with 0 minus 3i, my imaginary component is negative, then we're down on the imaginary axis, or the y-axis, and my angle measure there is 3 pi over 2. Overall, therefore, the complex number a plus bi has what we say complex polar coordinates of the modulus of z and the argument theta, with r greater than or equal to 0 and theta to be between 0 and 2 pi. This should draw very direct parallels to what we developed in the polar coordinate sections where we say that we have polar coordinates r and theta. And it will work in the same way.